of interacting stochastic populations. And this is based on joint work with Alex Henning at Tufts University. Phan at Quang Binh University, and my former PhD advisor, Joachim. Okay, so I will talk about the formulations, and then we will discuss some properties of the value function. And next, we will introduce the numerical scheme to approximate the value function and optimal control. I will discuss some special case and then provide some examples. So please stop me whenever you have questions. Okay, so we start with a single species model. You have xt is the population size at time t. We have b, the growth rate, and a is the interactions coefficient. I believe everyone is familiar with this population model. And now we consider the noise. So population systems are often subject to environmental noise. And we introduce the noise to the model by considering B, and we replace B by B plus Y noise. So Y noise is considered as the derivative of the Brownian motion. So if we replace B by B plus Y noise, then we arrive at the stochastic differential equation 1.3. So if you are not familiar with the stochastic differential equation, just take C equals 0. And if so, you just have differential equations. Oops. Yeah. Okay, so in this equations, Wt is a standard Brownian motion. So for convenience, let me remind, we have W0 equals 0. So we start from the origin, and the increment Wt minus Ws is normal random variable with parameter 0 and t minus s. And we have independent increments. Okay, so if we have a probability space omega and p, then for a fixed t, we have xt is a random variable, while for a fixed omega, we have a continuous function. So for each t, we have the value. So this is a continuous function. And if we consider x as a function from omega times 0 infinity to the set of real numbers, then we have a stochastic process. Yeah. So I'm talking about this special case, and then we'll generalize to our model. Okay, so let me show you some simulations for this single species model. Here we have 3 sample paths. Of course, we have noise. In this case, we have C equal to 1. So the path is non-smooth. Okay, so for these models, we consider several cases. If we have small c, so c is the noise intensity. So if we have small c, then the species is persistent. And if we have large c, then it's extinct. So on the graph, you see if c equals 0, we just have, this is the solution of the of differential equations we are familiar with. And if c equal to 1, the species is persistent in blue, and if C equal to 4, then the species is extinct, and you have the rest one. Okay, so for a system of two species, we consider comparative case. If the noise intensities are small, then both species are persistent. If in this one we have the noise intensity of the second one is small, of the first one is large, then the first one is extinct and the second one is persistent. And in this case, when the noise intensities of both species are large, then both species are extinct. Yeah, so we just look at some stochastic population system, and we have many papers devoted to these theories. Now, we introduce the problem we are interested in. So for the zero ecosystem of these species, we denote XIT, the population of the species I, and we denote by this, by S, 0 infinity to power D and S bar. And we consider a population system given by stochastic differential equation 1.4. Okay, so now we'll introduce the control and our objective. So we have YT is one control and ZT is another one. So Y is the harvesting components and Y and Z is the seeding components. So Y means we harvest. So we harvest, and Z means we add, we renew, or we seed. We buy species and then we add into the ecosystem. So both YT and ZT are non-negative. Okay, so we introduce the price function. For harvesting, we have the price is denoted by F. And for seeding, we have the cost denoted by GI. So we have the performance function or the reward function given by 1.6. So the first component is the amount, say amount of money we have from harvesting. So like we harvest and we sell for money. And the second component is the amount of money we pay to buy species and to renew the given system. Okay. So so our objective is to maximize this functional, this performance function. We want to maximize this performance function. So we want to find the optimal control Y and Z. And in order to do that, we define the collection of admissible control. So roughly speaking, we want to make sure that the y and z are non-negative, and we under our control we have a unique solution, and this is a global solution. Yeah, and the harvesting problem is to maximize the performance function, and we find optimal strategy, optimal control in the class of admissible control. So this is the problem we are working on. We require some assumptions. B and sigma are local ellipses continuous, so that the system has a unique global solution. And for the price, we require that the price is smaller than the cost. This is because in our work, we consider that it's harder to seed, it's harder to renew. So when you want to renew, you have to buy species and you have to do further action to seed. Because of that, we suppose the price is smaller than the cost. Okay, so we mentioned some related works. So of course, the control problems we are working on is just a special case of some others control problems. But we focus on biology system, and we try to understand the biological interpretations of the result. So to mention just a few, we have worked for single species ecosystem. Some are old and some are very new. For interacting population, we have Lungu, Oxendo, and myself. A related problem is optimal dividend and capital injections. So this is, we have a very many papers working on this. For numerical methods for singular control, we use the Kushner approach. So Kushner is the advisor of my PhD advisor. Okay, and for renewable resources exploitation, we have some recent work by Carol B. So those are related works. And this talk is based on our recent papers in Journal of Math Biology in 2019 and 2020. Okay, now we will introduce our main results together with some numerical experiments. The first result we want to establish is the finiteness of the value function. Yeah. So to do that, we establish the part A of this proposition. So roughly speaking, if we can show that if we can find a C2 function satisfying this system, then that function is upper bound of the value function. So in particular, if we have 2.2, so if we have Bix less than or equal to the delta I plus C, then we can show that the value function is the sum of fi0 xi plus m. Now, of course, if we have other assumptions rather than 2.2, then we can try to establish further bounds. But for ecosystem, 2.2 is sufficient. Okay, and then we establish the continuity of the value function. So first we compare between Vy and Vx for 2 points in the S bar, and then we show that the value function is Lipschitz continuous. So this is a very strong result. The proof is simple, but the result is very strong. Okay, so another result is for viscosity solution characterization. So we show that the value function is a viscosity solution of the Hamilton-Jacobi-Bellman equation associated with the control problems. So we use the technique from the viscosity solutions approach to prove first that we have a sub-solution and then we have a super solution. Okay, so the point is that we want to analyze specific models. So we want to develop numerical algorithms or numerical approximation to solve this problem. And in order to do that, we use the Gerstner approach. We use the Markov chain approximations. So, okay, so our observation, first one is that the closed form solution, of course, is impossible to obtain except for very special cases, but it's still difficult. We can only provide maybe just a few special cases. And moreover, the initial value V0 is not specified. So V0 is mean we start with an empty ecosystem. So using the approach in Gerstner, the book by Gerstner, we construct a control Markov chain to approximate the XT. The control problems for Markov chain can be solved. And once we combine this, we can prove the convergence and we can apply the result to approximate the value function and the optimal control. Okay, so one more thing, when we work with numerical approximation, we need to work with a compact set. So we suppose that we have a large enough U so that the populations always in the compact set, 0U. So it should be 5 for ecosystem because for ecosystem, like the populations just around 0 and some up about. The chance that is go to infinity is very small. So we will take U a large number. Okay, now it's quite technical to construct a Markov chain. We will use a partition of the compact set 0 to U to power D. So each state have components KIH. So we have K1H, K2H until KDH. And so you have a state space SH. Okay, so in order to mimic the behavior of the original population process, we introduce harvest, seed, and do nothing. So we have three options: harvest, seed, or do nothing. And the action at step n is denoted by pi nh. So we have many options at a specific step. We might want to seed for species I, or we do nothing, or we harvest species I. So roughly speaking, we have 2D plus 1 options option at each step. The amount we harvest and we seed at a specific step is H. So if we harvest species I, then we will harvest an amount of H. And we do not seed in that case. Okay, so we have a sequence of control actions. So we are trying to mimic the behavior of the original population system. So we use the Markov chain to mimic the behavior of population system. Okay, so the next step, we need to define the transition probability together with the control, admissible control. So we introduce admissible control for the Markov chain. And this is just the translation from the continuous model to Markov chains. So it's not a big problem. So let me just go this. Okay. Now we have the Markov chain. And in order to prove the convergence, we need to construct the interpolation. So we need to find a continuous, say, interpolations of the Markov chain to prove the convergence. For that, we need to introduce the interpolation intervals. Okay, so once we have the interpolation intervals, we define the performance function for the Markov chain. Oops. This is just the translation from the continuous formula for the Markov chains. And this is the value function of the control chains. So now we want to maximize the performance function for the Markov chain. Okay, so here we have the transition probability. Okay, so roughly speaking, under this transition probability, the Markov chain we are constructing will be approximating the original population system. And actually, Kushner already suggests some steps in order to get this transition probabilities. Okay, and the main result is that if we let h go to 0, then the value function of the Markov chain will converge to the value function of the original continuous problems. And this also allows us to construct the near optimal control for the given problems. So the proof is technical, but Basically, we use the weak conversion methods, weak conversion methods of probability theory to establish the conversions. And along the way, we need to introduce the times rescaling and we need to construct the continuous time interpolations of the process. So I will skip this. Okay, so now I will introduce some other formulations. So in the previous, in the original model, we have YT and ZT, Y and Z, and they are singular control. So now we consider the case we have regular control. So suppose we only have the bounded city or the bounded harvesting. So in particular, we suppose we just have the bounded city. In particular, we have the ZT is equal to CIT times DT. So you have this DZIT equal to CIT times DT. So CIT is the seeding rate, and the seeding rate is non-negative, but it's less than or equal to lambda I, for given lambda I. So in this case, we are able to combine Z and the drift components, and we just have one singular control lab. So you have one regular control C and the other one singular control Y. So we revise the performance function and the value function. Yeah. So this problem, we are able to solve this by using the same methods as we used for the previous formulation. This is about this seeding, and we can also consider the bounded seeding and the harvesting. So that means we suppose the harvesting rate and the seeding rate are bounded by, say, lambda I and mu I respectively. So in 4.4, we no longer have a singular control. We only have two regular control here. And we can also combine C and G as a regular control only. So we will consider, we revise the performance function and also the value function. And we are able to use the methods in previous section for this problem. Okay, so I feel that I will finish early. Okay, so now we'll look at some specific examples. We use the numerical methods in the previous slides to approximate the value function and the optimal control. First, we look at this. This is a single species ecosystem. F is the price, G the price when we harvest, G is the cost we seed, and sigma is the noise intensity. So this gives us the value and also the policy. So as you see in this case, you have a V0. V0 is positive in this case. So V0 means we start from an empty system, empty ecosystem, nothing. But we buy things, we buy species, and we establish the system. And then we get V0 positive here. V0 here is about 8.1 or so. Now for the optimal control, if X is small, we seed. If X is very large, then we will harvest. So 1 means we harvest, and -1 means we seed. And if X is in the middle, then we don't do anything. We just wait. So if we start with an ecosystem, like in this form, then eventually we'll keep the population between, say, L and U. So L is the lower bound and U is the upper bound. And if the population is smaller than L, then we will add. And if the population is higher than U, then we harvest. And this is the what we observe for single species ecosystem. In this case, we consider the same model. The new point is that the G equal to 50. That means the cost of seeding is very high. And if the cost of seeding is very high, we will not seed. Okay, so now we just have we just choose two options. If the population smaller than some level, say L, then we don't do anything. If the population is higher than L, then we harvest. So if the population is higher than L, then we will harvest. So the point is that in this case, we are allowed to seed. We are allowed to renew, but we don't do that because the cost is too high. Okay, so this is the case. We still work on that model, but we consider sigma equal to 500. So you see sigma is very large here. This means the noise intensity. Now, if the noise is very large, then we already observed that the species is extinct. So xt converts to 0 quickly. Because of that, if you look at the value function, then you see that this value function is just like the function fx equal, is just like v equal to x. That means we harvest immediately. And we also observe that the harvesting level now is smaller than the preceding example. In preceding example, we harvest later. Now we harvest earlier because the noise is very large in this case. Okay, so now we'll look at some two-dimensional ecosystem. In particular, we look at the competitive system of two species. The upper bound of harvesting and seeding rates are given here. So that means this is for harvest. So we are allowed to harvest at any rate we want. But for seeding, the maximum rate is 0.5. And so let me show the graph. So this graph tells us the domain of harvesting, seeding, and doing nothing. So there is a curve. So this is the gamma curve. And if the population is above the gamma curve, and you see in this part we harvest. If the population is below this, then we seed or we don't do anything. We seed only the green part. So for green part, we see species 1, and for the other part below the curve, we don't do anything, just wait. And we just seed species 1, not species 2, because in this case, the system is in favor of species 1. Okay, and this is the last example. We have a predator-prey model with the functional response. So as you see, we have the harvesting and seeding rates the same as our previous example. So the model is different because here we have predator and prey. So Act 2 is the population of the, okay, so the predator is here for Act 2. Okay, so let me show you the numerical experiments and the figure we get here. So similarly, we also have a curve gamma, and if the population like above this, then we will harvest. And below this, we don't do anything. We only seed the prey, not predator. And the shape, if we look at the shape of, so if you look at the shape of the curve gamma, then this is the previous curve, and now I show you the new curve. They are different in the shape. So it means we try to keep the population of the predator very low. So because this is predator-prey, two species have different roles. If we compare with the previous system, we have in the comparative system, two species, you have the same role, but now we have different roles in the system. And I think this is the last frame. Yeah, thank you very much for your attention.
Thank you very much, Dr. Changki. Do you have any questions for our speaker? Oh, I don't hear anything. I have one question, maybe two. The first one, like in the last slide, you say you consider a situation for two kinds of species, right? So, but actually, your model would be extended for maybe 3, 4, 5 species.
Yes, you're right.
And the method would be the same, right? The same method.
Yeah. So the method could be the same, but because when we look at the biological interpretation, then of course we always start with the comparative predator prey, And actually, if we look at one species or two species, then we will see it's easier to observe things and to get the biological interpretations. Yeah.
I see, but maybe for two species, the situation is like, I would say, not difficult, because for more than two, you have to decide which one you harvest or which one you have to sit.
You're right. Yeah, yeah.
You have to determine the priority, right?
Yeah, yeah, yeah.
Yeah. So, okay. The second question is about application of this. So, have you seen some kind of real application of such model?
Oh, so there are thousands of papers looking at applications of this. Yeah.
No, I mean, not about papers.
I mean, yeah. I mean, not this paper, but we are on the stream. Yeah. So this is just a special consideration. We have thousands of related formulations, not only for the system ecosystem, but also for natural resources management. And actually, people apply this for various model for like fish harvesting and things.
Yes, yes.
Yeah, but actually, in our references, and we also mentioned some work, but uh, this is not our objective. So we try to apply the mathematical result to get inside the result first. Yeah.
Okay. Yeah, I think in big countries like Russia or US, in very big farms, sometimes they have some automatic system, so that have to determine, what time, the time to harvest of seed, whatever. I think maybe such machines were created based on such models, right?
So that I already reached many research papers. Yeah, but I'm not, to be honest, I'm not sure if this is what people use in practice. Yeah. I mean they have some argument, and even I know that, like, I have some discussion with some people about possible applications. Uh, I mean, I mean, one people is kind of they really want to see this. I mean, the graph when we determine the domain, yeah, and this is what people want to see. So the domain in which they where they keep or where they harvest, and they want to determine the rate. But the point is that this is their work. So somehow it's technical to understand, because it's not just mathematical stuff. Yeah.
Mm-hmm. Yeah, I think I'm just curious about application of such model. I think it should be applicable somewhere. Yeah. All right. Do you have anything else for our speaker?
Can I ask a question?
Oh, yes, please.
Oh, okay. So I'm not familiar with the ecosystem, and also even the terms harvesting, seeding, those terms I'm not familiar. I'm curious. You mentioned the Markov chain approximation, and I'm wondering what are kind of operational technique or software you are using to get your model.
You mean the software I use for the numerical experiments, right?
Right.
Yeah. So this actually for the code is we can run on any software package. I use R in particular. I'm familiar with R, but my colleagues, they use Python. Yeah.
That's what I'm guessing, because in R we do have lots of the Markov chain approximation.
Yeah.
Okay. Thank you.
Okay, thank you, Hujun, for the question. Do you have anything else for our speaker? So if not, please thank our speaker again for his interesting talk. And thank you everyone for being here today. And we'll see you next week.
Yeah, thank you very much for your listening, and thank you, Dr. Hua, for inviting me to give this talk again. Yeah, thank you and see you. Yeah.
Thank you. Thank you.